We have two types of optimization, unconstrained and constrained. We have discussed also about the application, and then we proceed with the basic form of optimization in quadratic form, where we identify their matrix notation. Okay, we understand the characteristic of definiteness. Is it positive definite, semi-definite, negative definite, and we have further our discussion on several variable function, where we have more than two variables, and we discuss about the definiteness of several variable function by using Hessian matrix, right? So the definiteness of Hessian matrix will define the maximization or minimization of the function. Okay, so now we are we're going to proceed with the Lagrange multiplier. Okay, so what is Lagrange multiplier here? Okay, so remember we have two types of optimization, right? We have two types of optimization. The first one is what? The first one is constraint optimization, and another one is unconstrained optimization. So let's take a look at our CI. We are going to discuss about unconstrained and constrained. So for this Lagrange is the basic theorem for constraint optimization. So let's take a look at the constraint optimization first. And then after this, we're going to proceed with unconstrained. There are a lot of methods in unconstrained. Okay, let me share you the CI first, so that we are on track. Okay, so we have done with the basic calculus there. We have discussed about the directional vector and gradient, positive, negative, definite, concavity, and convexity. So before we proceed with unconstrained, so let's just surfacely discuss about the constraint, okay, where we have how many methods for constraint? Not so much, right? 1, 2, 3. Three methods for constraint, and then the rest are for unconstrained. So let's discuss for constraint here, where we use Lagrange multiplier. Okay, so what is Lagrange multiplier? As you can see here, Lagrange multiplier is to obtain, okay, is used to obtain the relative minimum or maximum of a function, okay, such that g, we have a function of g equals to b, where k equals to from 1 to m, all right, form a function. So this one is the theorem of Lagrange multiplier. We have a function that we want to understand its maximization or minimization, and we have a constraint. Then the Lagrange multiplier will combine the usage of f and g here in fx lambda, where fx lambda here equals to fx minus bi minus gi times with lambda k. This is for constraint. Okay, this is a constraint. This is for the function itself. Let's take a look at the example after this. And we can solve simultaneously n plus m equation here, del f del xi up to del f del lambda k. We are going to find the critical point of x1, x2 up until xn, and lambda 1, lambda 2 up until lambda n. Okay, so f here, this f here, we call it as Lagrangian. Okay, the Lagrangian, and the parameter lambda is Lagrange multiplier. So this is Lagrange multipliers. All right, so note that this is a necessary condition, and the solution needs to be checked to determine whether the solution is maximum, minimum, or no extreme point. How can we check? By using level curve, or where we understand about their neighborhood point. Okay, I'm going to show you after this. And another one, we can check X Hessian. Okay, once we got the critical point, we need to check, okay, the solution. Is it maximum, minimum, or no extreme point? How can we check? By using these two methods. All right, we can check the level curve, or we can check by using Hessian. So the Lagrange multiplier is used to transform the constraint optimization to unconstrained. Okay, so basically, even though there are two types of optimization, unconstrained and constrained, okay, but for constraint, we can convert to unconstrained by using this Lagrange multiplier. That's why our main focus is for unconstrained, because for constraint itself, we can convert to unconstrained. Is that clear, everyone? Okay, so let's take a look at this. The first example here. We want to maximize, okay, we want to maximize function x1 squared plus 4x squared, 4x2 squared, okay, such that x1 plus 2x2 equals to 6. So this is the constraint. Okay, so first, in order to use the Lagrange multiplier, what we need to do is by using this f. Fx lambda is a combination of x okay, fx equals to what? Fx is x1 squared plus 4x2 squared. Okay. Wait. Then we have what? Minus, right? Minus the summation of lambda. We have how many constraint? One constraint, so lambda 1. Okay, and then bi minus gi, which is what? 6 minus x1 minus 2x2. This is obtained from the constraint. All right, you got it? Okay. So the next part is we need to solve simultaneously, okay, the equation where we have to have del f, del x1. We have xi here from 1 to 2 only. So del f, del x2, and another one is del f, del lambda 1. So we have one lambda, no need to have lambda 1 there. Okay. So try to differentiate this. Got what? What is del f del x1 there? We have what? 2x1, okay, plus lambda, okay, and then del f del x2, we have 8x2 plus 2 lambda, and del f del lambda, we have x1 plus 2x2 minus with 6. Okay. All right, everyone got this? First, we convert to this Lagrangian f. Okay. First, we convert to f. And then we introduce the Lagrange multiplier lambda here. Okay. Then we apply the necessary condition to find the extremum point where we need to have the critical point. So in order to have a critical point, remember the first derivative equals to 0. So first we identify all the first derivative of each variable and then equate them to 0. And what we need to do here is to solve simultaneously of the equation in order to understand, in order to obtain the value of x1, x2, and lambda there. Okay, try to figure out the values. So we have 3 equations there, right? Okay. Understand or not, guys? Understand what is this Lagrange multiplier is about? Doctor. Okay, so try to obtain the values here. You can solve it by using your calculator, right? This is up to only 3 variables, or you can use other software. Okay, got it, guys? What is x1? What is x2? Okay, good. So you have 3 over 2 and minus 6. Okay, so these are all the critical points that you obtain. And we need to check whether is this critical point is correct in order to give the function there maximize. Okay, so now let's take a look. How can we check? The first one, you just check the Hessian matrix of F. Okay, where we have discussed this earlier. Okay, so you just can check by using the Hessian. Okay, the next one, you can check by using the level curve. Okay, so now I'm going to show you here. How can we check by using the level curve? So first, x1 squared plus 4x squared. This is a circle, right? Where you have, this is how can we discuss the level curve there. Up to. And then we have x1 plus 2x. 2 equals to 6. This is the straight line. So now 3 over 2, x1 and x2 here. This is 3 over 2. And as you can see, the maximum of the curve can be, the local maximum can either be here, here, or here. And as you can see, the curve is, the critical point is located here. Where is it maximum enough or not? As you compare to the curve, to the highest curve here. Okay, is it maximum or not? The circle come from the function x1 squared plus 4x squared. Maximum enough, is it? Check box. Okay, so as you can see from the curve, okay, as I mentioned, the curve here is obtained from x1 squared plus 4x squared. And this is a circle where it can be up to here and here and here. And it can also be, okay, it is a level curve. In terms of level curve, it can be expanded to n curve. So if your critical point is here, it is not maximum enough. All right, because we don't want to measure up to the how many curve here? K equals to 1, K equals to 2, K equals to 3. That level curve can be can be any value. Okay, K equals to 4, K equals to 5. So this is on the constraint. Okay, as long as it is lower than the level curve, then we cannot say that it is a maximum. Okay, as you can see from this point and this point, the constraint is fulfilled. If you substitute x1 is 3 plus 2 times 3 over 2, it is equals to 6. The constraint is fulfilled. That's why the point is on the constraint. Okay, and then if you substitute to fx, right, we have 3 squared plus 4 times 3 over 2 squared, it can becomes 18. So the function here is 18, and we don't know is this 18 is maximum enough in order to fulfill the constraint. So that's why we can identify this from the level curve. Okay, if you use Hessian matrix, right? If you use Hessian matrix, you can check the definiteness of the Hessian matrix of the function itself. Okay, where fx equals to what? X1 squared plus 4x2 squared. Okay, Hessian matrix give you what? Can you construct the Hessian matrix from here? What is your Hessian matrix?
Differentiate f with respect to x1 and x2,
Okay,
and it is 0.
this one is x1 and x1, right? Okay, before you obtain the Hessian matrix, you have to have your del f del x1, del f del x2. Same with the previous one. We have here equals to what? 2x1, and then this one is 8x2, right? In order to form the Hessian matrix, we need to have, here is what? fx1, x1, fx2, x2, okay? fx1, x2, and fx2, x1 equals to what? This one, x1, x1 is 2, right? x2, x2 is 8, and this one is 0, right? So your Hessian matrix, this is your Hessian matrix. And then how can we check the definiteness? You need to check the principal, leading, successive, minor principal, right? Remember what we have discussed earlier? So let's say this is your your A. So A1 is given by 2, right? A2 is given by 2008. And this is a positive, and this one is also positive. Then if all leading minor principles are all positive, then we can decide the Hessian matrix is what?
Positive definite.
Okay, positive definite. So when it is positive definite, then the function, the critical point that you obtain is minimum or maximum? Minimum. So instead of using the level curve, as you can see from the graph, it is not shown that that is the most maximum point from the curve. And it is also proven in the Hessian. By using the Hessian matrix, you show that the critical point is minimum point. So the question here is the solution is valid for this case? Then the answer is not valid because it is show that it is not maximum enough on the curve, and by using the Hessian matrix, it is not a maximum point, it is a minimum point. That's why in Lagrange, okay, this is a necessary condition that the solution need to be checked to determine whether the solution is maximum, minimum, or no extreme point. All right, so that is the problem in constraint. We have to check. Okay, is that clear? Anyone has question? Okay, that one is for Lagrange multiplier. Okay, let's try another example. Minimize x1 minus 2 squared plus x2 minus 2 squared such that. Okay, try to use Lagrange multiplier. Okay, the next one is Taylor's theorem. Okay, so we have Taylor theorem, and also the next one should be directional vector and gradient. This is just an additional knowledge. You just can read it by your own. Okay, for theoretical proof. It is used in theoretical proof. Oh. Okay, now for Taylor's theorem, we use this Taylor's theorem for multivariable function. Okay, before this, we start with what? We start with univariable function, and then we have a quadratic form. Okay, so how can we identify the optimized solution for quadratic form? We check the symmetric matrix, and then we have several variables. We check the Hessian matrix. Okay, about the positive definite, or is it semi-definite, negative definite, indefinite? All of those definiteness give you a meaning behind that, right? So now for multivariable function, we still use the definiteness of Hessian matrix, but it involves some types of expansion, okay, in using this Taylor's theorem. So you can read this theory, okay. This is just for proving process, and the importance for Taylor's theorem is to build up the necessary condition in order to determine the maximum and the minimum. So still we are stick with our necessary condition in order to determine the maximum and the minimum previously, but for this Taylor's theorem is just to build up for more than for multivariable function. Same process. In Taylor's theorem itself, there is H there, and that H is a Hessian matrix. So we still use the Hessian matrix here. Okay, so from the Taylor's theorem, we can deduce that the necessary condition for the critical point x naught to be extreme point of fs if the Hessian is positive. Again, still we are using the Hessian. So if the Hessian is positive, then it is a minimum. If the Hessian is negative, then it is maximum. So this is the proving process. Okay, so the sufficient condition for the critical point to be minimum if and only if the Hessian matrix is positive, definite. So how can we identify the Hessian matrix? Just like we have done previously. Okay, this is only up to the extension of the theorem that we have discussed earlier. Is that clear, everyone? Yes? You raise your hand. Okay, so we have done with the basic calculus of optimization, the basic calculus that we're going to use in optimization. We have discussed the theorem that we're going to use and so on. And we have also discussed on how can we identify the maximum or the minimum point on constraint optimization, where we use the Lagrangian, okay, Lagrange multiplier. All right. Okay, before we proceed, anyone has question? Everything's clear? From 1 to 10, where are you for the first topic, the first chapter? Of course, it is quite theoretical for the earlier stage. Okay, we have done with this basic calculus, and I hope that you can try to understand and read again all the notes. Okay, theoretically, it is like that. Okay, after this, we're going to proceed with the numerical process in understanding the unconstrained optimization. Okay, all right, good. From what I can see, 7, 7, 8, 7, 6. All right, okay, thank you for the next one. Okay, now I have also gave you the notes on unconstrained optimization, right? 2A, unconstrained optimization. Oh, Fibonacci is 1. 2B, sorry. I did give to you up to Fibonacci, right? Okay.
Yes.
All right. So now the next one is, let's proceed with this 2A. Unconstrained. So we have discussed with constraint. Now it is unconstrained. All right. So next is unconstrained optimization. Okay. Before this, we have constraint. We use Lagrange. What is the purpose of using Lagrange? We convert the constraint to unconstrained. Instead of having such that constraint, we just combine the constraint by using the Lagrange multiplier to have one function. Remember, we have fx subject to gx. This is for constraint. And then we use Lagrange multiplier to have fx and lambda, where we combine fx minus with lambda times gx, b minus gx, right? Okay, so we convert constraint to unconstrained. So now it is unconstrained itself. Okay, so how can we understand about this unconstrained? Okay, the first method in solving the unconstrained optimization here is direct search method. Okay, so this direct search method are applied when we are facing some difficulties to find the derivative of the function. Okay, before this, we just convert, we differentiate, right? But now, where we are facing difficulties to find the derivative, Then we use this direct search method in unconstrained. So this method depends on the value of fx at points x1, x2, x, and then compare those values to optimum to obtain the optimum point. So as you can see, we have fx, okay, and then the methods depends at points x1, x2, xn, x3, x4, up until xn, until we reach the optimum point. What is the meaning by that? The meaning by that is we need to have some sort of steps in finding the optimum point. Maybe one iteration, maybe two iterations, up to how many iterations that you need to have until find the optimum point. Okay, understand? Then this method will reduce the initial interval to become smaller interval where it consists the minimum number. Okay, so let's say we have fx. Nota unconstrained tak ada. Tak ada. Yang ini tak ada. Tak. Sekejap saya tengok. Oh, terus Fibonacci. Okay, sorry. Apa ini sikit je. One page je. Saya bagi terus. Right. Or else I bagi through WhatsApp pun boleh kan? Sorry. One page only. Alright. Okay, let's proceed. So let's say this is your function. In order to gain the optimum point from, let's say from the initial point, we want to have optimum point. Okay. Let's say we want to have the maximum value. Okay, and let's assume that that is your maximum point. So we need to reduce the interval from A to B here. Let's say from here to here, and then from here to here, from here to here, from here to here, until we reach the maximum point. So from reducing the interval here, we will have some sort of iteration in our calculation. Okay, why? Because we just want to reduce the interval to become smaller and smaller until we reach the minimum or maximum. Some, let's say like this for minimum. This is just illustration. And then this one is for maximum. Okay, we want to reduce the interval until we reach the optimum solution. Is it maximum or minimum? Okay, understand? That is how we find the solution for direct search method in solving the unconstrained optimization. Okay, clear? Clear not? So why we need to have direct search method? Just like before, why just don't we differentiate and then identify the values from the Hessian or from the symmetric matrix, or we just can directly differentiate? Because this is applicable when we are facing difficulties to find the derivative. Sometimes the function is quite complicated where we cannot directly differentiate. Then we use this direct search method. Okay, why we use? Where a function is non-differentiable function. Okay, del f del x is not continuous and difficult for numerical evaluation. Okay, All right, time constraint, like complex algorithm need approximate solution. So instead of finding the exact equation, sorry, the exact solution, just like what we did previously, okay, exact point, one calculation, one solution, but now we want to use this direct search method in terms of numerical process, okay, numerical evaluation, okay, clear? So this is direct search method, okay. So in this direct search method, right, we have one-dimensional optimization methods. Okay, we have two methods. First, reduce the interval where the minimum number is located until the accuracy is attained, just like I explained here. We reduce the interval until the minimum or maximum number is located. Okay, approximation by a polynomial with lower degree to predict the location of a minimum function. Okay, in unimodal function has one maximum or one minimum, and the interval, the value of fx will reduce when the value of x is approaching. Okay, so the first direct search method that we're going to discuss is Fibonacci. Okay, Fibonacci method. So this is one method in direct search methods. Okay, remember direct search method, we apply the reducing of interval to find the optimum solution. Okay, why we have to use it? When the function is non-differentiable. And how we use it? We reduce the interval until we found the optimum solution. Is it minimum or maximum? Okay, is that clear? So this is just the explanation on direct search method. Okay, remember in our unconstrained we have many methods here. So the first one is direct search method, where it is one-dimensional search method. Then we are going to discuss about Fibonacci and golden search. All right, clear? Everyone's clear about this? But what I have been explaining? Okay, so what is Fibonacci method? Okay, I'm going to explain this throughout the example so that you understand. So this is the theory, okay, and the flow chart of the process. Okay, so in Fibonacci method, saya nak explain through the example. Sekejap saya letak dalam OneNote. The first one, you understand about what is the Fibonacci, one direct search method. So Fibonacci is one method in direct search method. Okay, so let's discuss on how we find the solution on minimization function by using Fibonacci. Right. Step 1, step 2, step 3, step 4. By the way, have you read this? Case A, case B, case C, case D. Okay, anyone has question before we proceed? Can you see the screen? Is it clear for you? Or is it too small? Okay, so now let's try to understand the first method, indirect search method, which is Fibonacci search algorithm. Okay, so first, this is for minimization function. Okay, too small. Okay, first, determine the initial interval AB and iteration and value of epsilon. Right, so now let's take a look at the Fibonacci stopping criteria at step number 6. So here, the number of n iteration is determined by this one, where when epsilon is too small, then it is approximately 0, then we have ln equals to ly L1 over Fn. So from here, ln over L1 equals to 1 over Fn. And this is less than epsilon. Okay. So how can we identify the number of iteration is by this? Okay. So when 1 over Fn less than epsilon, let's say epsilon equals to 0.03. So 1 over Fn less than 0.03, it can be Fn greater than what? 33 to the power of 1 over 3. Equals to what? 3 point something, right? So this Fn is determined by number of Fibonacci. Okay, Fn here is number of Fibonacci, where Fibonacci number starts from 1, this one. Determine number of Fibonacci based on the equation. Fibonacci number start with 1, F0 and F1 is 1. And the rest is Fk equals to Fk minus 1 plus Fk minus 2. So, Fibonacci number F0 equals to 1. F1 equals to 1. F2 equals to F1 minus F0. Sorry, plus. Referring to this, F1, Fk minus 1 plus Fk minus 2. So, Fk equals to Fk minus 1 plus with Fk minus 2. F2 minus 1, F1, F2 minus 2, F0. So, equals to 2. This is how you obtain the Fibonacci number first. Okay, let's discuss with how you obtain the Fibonacci number. F3 equals to F2 plus F1, which is 5. F4 equals to F3 plus F2, which is, sorry, this one is F2 plus F1, 3. This one is 5. Again, F5 is F4 plus F3 equals to 8. F6, F5 plus with F4, which is 30. And so on. This is how you obtain the Fibonacci number. How you obtain the Fibonacci number is referring to this formula. Why you need to obtain the Fibonacci number? Because we want to identify the number of iteration by looking at this. When Fn greater than 33 to the power of 1 over 3 here, we stop up until where? Again, let's proceed. F7 equals to 21. F8 equals to 34. F9 equals to 54 and so on. So now, as you can see, 33 to the power of 1 over 3 is located here. 33, not power, 33 1 over 3. Okay, it is located around here. So the number of iterations should be up to 8. So n should be at least up to 8 iterations. Okay, that is how you identify the n iteration, and value of epsilon usually is given, right? So this one, I give it to you about 0.03. Okay, so 1 divided by 0.03 is 33, 1 over 3. Okay, and once you obtain the value of Fn here, you can decide the number of iteration. Is that clear? Any question? Any question for this? So far understand, eh? Okay. First, determine the initial interval. This one usually is given. And then the value of epsilon is given. Then you can find the number of iteration where it is given by Ln over L1, which equals to 1 over Fn less than number of epsilon. So this is how you obtain the Fn. So if epsilon is given 0.03, then 1 over Fn less than 0.03. So Fn greater than 33.33. So looking at the Fibonacci number, then you can decide the number of iteration. Is equal or greater than 8? Is equal. Okay, at least is equals to 8. Why? Because we have take greater value compared to the Fn. Okay, we take up until 8 iteration. Okay, as you can see from the analogy that I have explained earlier, you want to identify the optimum solution, right? If it is maximum or minimum, you reduce the interval. Okay, the smaller the interval will give you what? The optimum solution. So as you can see from here, the number of iteration is defined by the number of Fibonacci. At least I choose 8. But if you choose greater than 8, of course, the solution is more optimized. But we need to understand about the time constraint. So let's just choose only up to 8. Okay, if you choose greater than 8, of course, the solution will be better. But there is a lot of time involved, right? For 8 iteration only, it is involved a lot of time. Okay, if you choose greater than 8, of course, then you will have no time in finding the solution. And usually we don't have to calculate up until 8. We just approximate the number of iteration. We decide the number of iteration, but in exam practice, just identify the number of iteration, and maybe the instruction is to calculate the optimized solution up to maybe 4 iteration, maybe 5 iteration. Look at the instruction. Okay, but theoretically, this is how you find the solution. Is that clear? Step number 1. All right, clear or not? Okay, let's just try the example. Okay, we do it one by one. Minimize x squared minus 6x plus 2 in okay, so this is example of problem using Fibonacci. Okay, now let's start with the first step. Determine the initial interval. So your initial interval is 0, 10, right? And then n iteration and value of epsilon. So value of epsilon is given, n iteration with the accuracy is less than 3%. So 1 over Fn less than 3%, 0.03. Fn greater to 33, 1 over 3. So at least 8 iteration is needed. So you identify the number of iteration and epsilon and interval. So this is your interval of AB. This is your n. This is your epsilon. Okay, that is for step number 1. All right. And then step number 2, determine the n number of Fibonacci based on the equation we have done with that part. Okay, Fibonacci number is at least up to 34 when n equals to 8. Okay, that is step number 2. You can refer to your notes. And then set x1 equals to A, x3 equals to B, L1 equals to B minus A, and compute L2. Okay, remember, L2 is given by this formula, but this epsilon is approximate to 0, then just focus on this part. Okay, and then x2 and x4 place symmetrically with the distance L2 from one end of the interval AB. That is x2 equals to x1 plus L2 and x4 equals to x1 minus x2 plus x3. So how can we do this? Okay, all right, refer to the notes. Let's discuss this. All right, so how can we do it? This is step number 1. This is step number 2. Step number 3. What is step number 3? Define x1, your initial interval is 0 and 10. Define x1 equals to A, x3 equals to B. So your x1 equals to 0, your x3 equals to 10. Okay, and then what? And L1 equals to B minus A. Okay, L1 equals to B minus A. So this is 10 minus 0. Okay, clear now? So initially, this is your line. From 0 to 10, L1 equals to 10. Right? So now, we want to have what? We want to have what? X2, L2, and X4. Okay? What is L2? L2 is given by Fn minus 1 L1 divided by Fn. L2 given by Fn minus 1 divided by Fn times with L1. Fn is what? Fn is 34. What is n? N is 8. So F8 is 34. N minus 1 is F7. What is F7? 21. So F7 divided by F8 times with L1. 21 divided by 34 times with 10. So L2 is given by, first what? 6.1765. So this is L2. Okay. Then from L2 here, you can have your X2 and X4. X2 is given by what? X2 is X1 plus L2. X1 plus L2, which is 0 plus 6.1765. So L2, X2 is 6.1765. And X4 is given by X1 minus X2 plus X3. Zero minus X2 plus X3, which equals to 3.824. So now, as you can see, in iteration number 1, so we have started with the calculation. Your initial line now becomes, this is 0, this is 10, right? Then your X2 is given by 6.17 and X4 is 3.8. And then calculate X. This is X4, this is X2. All right. So now, okay, guys, are you with me? Understand or not? We have done with finding L2. Okay, once you obtain L2, you need to have your X2. Okay, and X4 is obtained by X1 minus X2 plus X3. Now you have all the values X1, X3, L2, X2, and X4. So in the line, just identify the position of the value, even though X2 is X2, but the value is 6.176, so it is located here. Okay, and then X4 is here. This is your X1, this is your X3. And L2 is actually the difference between X1 and X2 and also X4 and X3. So this is L2. Okay, now we want to identify the next iteration. Okay, look at the notes. Okay, step we have done with L2, X2, and X4, and then evaluate Fx2 and Fx4. We have evaluate the Fx2 and Fx4 here, Fx2, Fx4. Then, in order to determine the next iteration, we need to check. Determine the new uncertainty interval by considering cases. So let's take a look at the cases here. Need to understand. When x4 less than x2 and fx4 less than fx2, your new interval is x1, x2. Okay, look at your value. Now, x4 and x2. Which one is greater? Which one is smaller? How to get F7? How to get F value is defined by the Fibonacci number here. This is the general form of Fibonacci. We start with F0 equals to 1, F1 equals to 1, then just proceed with the formula here. Okay? So now, how can we check the next interval is by looking at the value of F. So when F, you have to check here, Fx2 is greater than Fx4. Okay, when Fx2 is greater than Fx4, you need to check the case when Fx2 is greater than Fx4. So we have this case A or case B. Then you check the value of x4. Okay, you have fx2. You check the value of x4 here less than x2. x4 is 3.8, x2 is 6. So x4 less than x2, then case A. Then the new interval is x1, x2 means that your new interval is x1 and x2. What is the meaning by the new interval? Means that your iteration at iteration number 2, your new interval is 0 and 6.176. The new interval is defined by A and B, which is x1 and x3. Again, we repeat the process of finding one by one from here. Is that clear? Is it fixed? Yes. Fibonacci number is fixed according to the formula of fk minus 1 plus fk minus 2. Okay, anyone has question for iteration number 1 here? Okay, so now let's take a look at the next iteration. Yes, if we want to find the optimum solution, we need to repeat until I equals to 8 because we define already the number of iteration, right? But usually in terms of exam practice, we just, okay, calculate this up until 3 iteration, up until 4 iteration. We just want to evaluate the steps that you have done, right? Okay, so now let's proceed. We have the new interval. Your new interval now is from 0 to 6.176. This is your x1. This is your x3. Let's take a look at the first interval. From 0 to 6.176. Is there any point there? We have 3.824, right? Understand or not? Guys, are you with me? Understand? Now, your new interval is from 0 to 6.176. Okay, which is, this is your x1, this is your x3. Let's take a look at the interval, the previous interval from 0 to 6.176. Is there any other point between them? Which is x4. The previous one, x4 equals to 3.824, right? So that is your new x2. So now x1 is 0, x3 is 6.176. From the previous interval, you know that your x2, which is the middle, is 3.824. What you need to do in the next iteration is to understand the previous interval and just update x4, where x4 equals to x1 minus x2 plus x3, and locate again and find fx1, find fx2 and fx4 and compare to get the new interval. Is that clear? So what is your x4 here? All right, 2.352. Okay, so 2.352. So the location of 2.352 should be here, right? This is your x4. So now you just need to evaluate what is your fx2 and what is your fx4. Okay, fx2 is given by negative 6.321 and fx4 equals to negative 6.580. As you can see, fx4 now less than fx2. When fx4 less than fx2, look at the case fx4 less than fx2, either case A or case B. If x4 less than x2, we choose x1, x2. x4 greater than x2, we choose x2, x3. So now x4 is 2.3, x2 is 3.8. So x4 less than x2, right? x4 less than x2, again, choose case A. Yeah, then your next interval is x1, x2. So iteration number 3. Your new iteration should involve the new interval of x1 and x2. Right? x1 and x2, 0, 3.824. So you have your x1, you have your x3, you can identify your x2. So now your new interval is from 0 to 3.824. And you know from here to here in the middle we have 2.352. So this is your new x2. Is that clear? And as you can see, the interval now becomes smaller and smaller from 0 to 10. From 0 to 10, from 0 to 6.717, now it's from 0 to 3.8. Can you get the idea? Understand or not? Then just update the process again. x1 minus x2 plus x3, identify your fx2, fx4, and then check the value. And then compare again, look at the case, and so on. Okay, so as you can see here, we just only need to calculate once of L2. This one, only one calculation. And the rest, you just need to take a look at the interval that you obtain one by one for each iteration. Understand or not? Is that clear, everyone? Oh, yeah, yes. For this case, we do the iteration 8 times. Because we have decided the number of iteration is 8 based on the epsilon value given. Okay? All right, why don't you try? Proceed up until iteration number 8. What you need to understand is the interval here, the interval process. Okay, anyone has question? The crucial part is at iteration number 1, right? We have to understand the interval, value of L2, and then the rest you just need to update by looking at the value of fx4 and fx2. Okay, clear? Okay, please proceed. Okay, right now I just want to discuss up until iteration number 8. Okay, please proceed. How many iteration we have to do? Again, 8 iteration because it is calculated here. When fn greater than 33, 1 over 3, then we check the number of Fibonacci. 34 is at n equals to 8. So at least we have up until 8 iteration. Okay? Just like I told you, theoretically, we need to do up until 8 iteration. But for exam practice, usually just calculate up until 4 to 5. Depends on the instruction. Okay, if it is not mentioned, then just proceed with the calculation until the solution. Okay, until the solution point. Okay, now, please proceed up until iteration number 8. So I just want to give it to you, the solution. In iteration number 8, what you should get is the new interval is 2.928, 3.232. So here we have 2.928, 3.232. Your x2 is x1, x3. x2 2.944 and just update the value of x4, which equals to 3.216. Okay, so as you can see, in the last iteration, the difference between fx2, even though it is smaller than fx4, is quite small. Okay, we want to reduce the difference between the function. It is quite small already, so it reached the number of error epsilon there. Then the minimum point is equals to x2 negative 6.997, which give the, sorry, this one is 2.9. 2.944, which give the minimum solution is negative 6.997. So this is how you obtain the minimum point with the minimum solution. Okay, the process is quite similar with the previous step. Okay, the crucial part is in iteration number 1. Right, and then you just repeat the process. X1, X2, take the value in the middle as your X2, find X4. Again, compare the values, check the next interval by looking at the cases here. Okay? If we didn't know the iteration, we need to solve until, yes, by cases. You should know the iteration because for Fibonacci, the iteration number is defined first by looking at the epsilon. Okay. So let's discuss about the benefit, the advantages of Fibonacci. Okay, the advantages of Fibonacci is only one function of L2 is needed, right? Only at iteration number 1, where we have to evaluate the L2. Okay, and then the accuracy is given in terms of epsilon and in terms of number of iteration. Okay, so when the iteration is fixed, then the optimum solution is also fixed. That is the benefit. In general context, maybe know the difference of other methods such as Euler-Taylor. Okay. Then after this, you can compare, right? Okay, so that is the benefit of the advantages of Fibonacci, where we only need to calculate once L2. The number of iteration and accuracy is also fixed, which is given. All right. And once we fix the number of iteration, then the optimum solution is quite easy to be found. That is the benefit. Okay, but some sort of disadvantages, we have to choose. The number of iteration depends on the epsilon. If we have smaller epsilon, then we will have more number of iteration, which is quite time consuming, right? That's why manually it is quite time consuming. Okay, that is one of the disadvantages. Okay, is that clear? After this, I'm going to give you the tutorial. I'm going to share it with you in the e-learning. So you can try. But for the moment, please proceed with the iteration here up until iteration number 8 on until you reach the solution point. Is that clear, everyone? So this is Fibonacci method. Okay, so for this optimization method, of course, you need to have a lot of practice. Okay, the calculation process here, you need to be very careful. The choices of values of x2 there, once you're wrong with the choices, then there should be a problem in finding the solution point. Is that clear, everyone? Anyone has question? Okay, Fibonacci method from 1 to 10, where are you? All right, good. Okay, so I think that's all for today. Okay, so for this Fibonacci, I'm going to give you the exercise after this. Let me type it first. I have a version of non-typing solution there. Okay. So no more question, I think. Right. Okay, so Alhamdulillah, we have done with the first method in